Hello everyone, this is Adman Al Fayaz along with my group mates Habib Tahmid Hussain and Qazi Zubair Ahmed. So we will be discussing on a topic regarding the antifouling coatings on a marine propeller and the effects of cavitation and the impact of the energy along with the efficiency. So we have arranged our entire project into several outlines, which includes introduction, objectives, problem overview, methodology, results, and conclusion. So in terms of introduction, so we know that marine propeller is one of the most vastly used in the marine vessels, and it is a type of rotating device that is helpful to propel the marine vessels through the water. And there are some basic design strategies while constructing a marine propeller, which includes the hub and the several blades depending on the size and depending on the properties of the marine propeller. And the pitch number of the marine blades propeller can vary depending on some specific applications, and it can vary depending on the type of the vessels. So there are some few objectives to come through before going through the project. The first one is we have to know what is antifouling coatings. We have to have some basic knowledge on antifouling coatings before going through this thing, so which helps to reduce the cavitational effects on the propeller. The second one is we have to put both of the propellers into a simulation with some different boundary conditions and some different simulating conditions, which includes a multi-phase condition and a non-multi-phase condition. And finally, we have to observe the outcome of our cavitation as well. So the problem overview is been very much in context with the marine propeller, as we can see that the seawater, which is highly corrosive due to its high salt content. So when the propeller operates through the water at high rotational speed, there are some changes in pressure which helps to corrode the propeller surface, and that usually damages the interior surface of the propeller. And also the microorganisms like bronchioles, algae, and mollusks can attach themselves to the propeller, and this also causes the local corrosion. And for this reason, there are some chemical interactions between the surface and the outer fluid of the water, and that helps to reduce, to enhance the damage level of the propeller on the surface. And in terms of methodology, we have designed two specific propellers based on some geometrical parameters. The one on the left has been selected to simulate under a non-multiphase condition. The one on the right has been selected to simulate under the multiphase condition. And these are all has been designed in SolidWorks, and these will be exported to the ANSYS fluid flow simulation to simulate the further outcomes. And the next topic shall be presented by my other groupmate Qazi Zubair Ahmed, and I'm requesting him to take the floor. Thank you.
Thank you, Faz, for the floor. Uh, the first one has been matched with concert effort to amplify the mass density accumulated in the realization of an inspiration array of 555 elements. Each constitute a finite and precisely calibrated unit that simultaneously interlocked with its neighboring elements. The section of an element size of 0.2 meter serve as a strategic choice, meticulously tailored to strike a harmonious balance between computational efficiency and the indisputable need to discern fine-grained flow characteristics. The jurisdiction chose amplified a commitment to achieve an optimal compromising where the computational resources were DeFi allotted to ensure both accuracy and computational transparency. The mesh computer cells a type of finite element commonly used in fluid dynamic simulations. The decision to use static cells is often driven by their flexibility in capturing complex geometries. In this case, the mesh is quite refined. contained a total of uh, 531,620 elements. This is high element count indicates a detailed representation of the turbine geometry, crucial for account capacity in the intrinsic flow pattern and behave around the blades. Considering that the simulation involves a multi-phase flow where multi-fluid phase coexist. Two distinct element sizes have been defined in the mesh. The choice of different element size allows for a tailored approach to accurate capture the characteristics of both the rotation domain and the propeller. In the undertaking analysis, a pressure-based transit simulation has been executed focusing on the first three-blade propeller. The simulation involves the application of essential boundaries conditions to model the dynamic behavior of the fluid around the propeller over time. The choice of a pressure blade approach implies that the solver is solving for pressure and subsequent velocity fields are updated to enhance the accuracy of the simulation. The SSD K omega turbulence model has been employed. This particular model is known for the capability to predict boundary layer behavior accurately and facilitate the transition from laminar to turbulent flow. Is noteworthy that the SSD-K omega model adopts a two-layer approach for a near-wall treatment, ensuring a more precise resolution of a flow in approximate to solid surface. This level of resolution is particularly crucial in the propeller simulations, where the fluid flow near the blade surface undergoes significant velocity gradient and formula vertical structure. The initial condition for the simulation involves setting the fluid in inlet condition to a velocity intake with a specific velocity of approximate 40 mph. The propeller rotational speed, a crucial parameter in such simulation, has been defined as 900 rpm. For the fluid outlet condition, a pressure outlet has been employed. The stability, the convention of the simulation are facilitated by the utilize the semi-implied method for pressure-linked equation algorithm. This algorithm is chosen for its stability characteristics and its ability to coverage towards a solution predicted.
Hello everyone, now I'll be discussing the results. So, examining the velocity contour illustrated in figure 7 reveals significant observation regarding the behavior of the propeller at a rotational speed of 900 rpm. Notably, the propeller experienced elevated velocity levels at the edge of its blades, a phenomenon attributed to the thrust generated by the propeller's rotation. Additionally, regions proximate to the rotating domain exhibit high velocity magnitudes. The heightened velocity at the blade edges are a consequence of the pressure differential between the front and back side of the blades. This pressure difference induces a net force propelling the fluid in the direction aligned with the propeller's rotation. As a result, fluid motion intensifies, leading to increased velocities in the proximity of the propeller blade regions. In essence, the velocity contour analysis provides a clear depiction of how the propeller's rotation influences fluid dynamics. The pressure disparity across the blades generates a propulsive force, culminating in a pronounced fluid motion with elevated velocities. Understanding these velocities patterns is critical for assessing the propeller's performance and comprehending the intricate dynamics governing fluid flow around the rotating blades. For the non-multiple phase model, in the left side, figure 8 depicts different pressure contours at all possible regions in the propeller blade. There is a sudden pressure drop at the leading edge and at the tip of the propeller blade as observed from the static pressure contour. As cavitation is typically associated with the regions of low pressure, In the pressure contours of this propeller blade, the total and static pressure at the sharp edges, including the leading edge and tip, is significantly lower than the surrounding regions. These low pressure areas indicate the potential for cavitation at high RPM. By keeping the same boundary conditions in both of the propeller cases, to understand the effect of cavitation, the updated propeller model has been simulated transiently where propeller has been operated for 7.5 seconds at 900 RPM. As the water temperature in the simulation is 25 degrees and the vapor pressure of water in room temperature is 3.17 kilopascal, all the negative pressure zone at the trailing edge during different times shows the phenomenon of cavitation as the pressure at different time stages. On the other hand, for the right-hand side picture, the Schneider cavitation model is selected to accurately capture the cavitation effects within the fluid. This model is known for its capability to predict cavitation onset, vapor distribution, and pressure fluctuation. The decision to turn on the multiphase model indicates that the simulation considered the coexistence of multiple phases, likely liquid and vapor. This is crucial for capturing the dynamic behavior associated with cavitation. The simulation is conducted over a 5-second period, allowing for the observation of the cavitation phenomenon at different time stages. This time-dependent analysis is essential for understanding how cavitation evolves and propagates over time. The vapor volume fraction, a key parameter in cavitation simulations, is visualized using isosurface. By initiating the vapor volume fraction from isosurface, the cavitating zones can be clearly observed and analyzed at different time steps during the 5-second simulation. Utilizing isosurface for vapor volume fraction provides a three-dimensional representation of regions where cavitation is occurring. The visualization method allows the researchers and engineers to identify specific area within the fluid domain where the vapor content reaches a critical threshold, indicating the presence of cavitation. The simulation using the Schneider cavitation model and the multiphase approach can build a detailed examination of cavitation phenomena over time. Visualization through isosurface of vapor volume fraction offers a comprehensive understanding of cavitating zones at different stages during the 5-second simulation, providing valuable insights into the dynamic behavior of the fluid around the propeller. Turbulence kinetic energy plays a vital role in fluid dynamics as it represents the energy stored within the chaotic and unpredictable turbulent eddies, making it a key parameter in the study of turbulence and turbulent flows. In the context of a marine propeller, the turbulent kinetic energy assumes particular significance as it can significantly influence the propeller's efficiency and performance. A marine propeller exhibiting high turbulent kinetic energy indicates a substantial presence of turbulence in the fluid flow surrounding the propeller. The heightened turbulence can have diverse effects on the propeller's operation, presenting both challenges and potential risks. Local pressure fluctuations arise from the turbulent flow pattern, resulting in areas diminishing pressure that could potentially instigate the formation of cavitation characterized by the creation of vapor bubble within the fluid. Cavitation being detrimental to the propeller structural integrity, may inflict damage on its surface and undermine its overall performance. Furthermore, high turbulence kinetic energy can lead to various flow rate consequences that negatively impact the propeller's efficiency. This include uneven loading on the blades, interference with the wake flow, heightened drag, and other flow-induced effects, all of which can compromise the propeller's thrust generation and propulsive efficiency. To gain deeper insights into the distribution and intensity of turbulence, kinetic energy around the propeller blades, Figure 9 and Figure 10 provides a contour visualization of the turbulent kinetic energy on the propeller for both the conditions. Both the figures showcase the trailing section of the blade experience the maximum turbulent kinetic energy, contributing to the formation of excessive low pressure zones due to pressure fluctuation. This observation emphasized the importance of understanding the intricate interplay between turbulence and pressure dynamics in propeller flow fluids. As such, knowledge informs design considerations and optimization efforts to mitigate adverse effects and enhance overall propeller performance. The turbulent kinetic energy in the context of fluid dynamics, including propeller simulations, is a measure of the intensity of turbulence within the flow. Turbulent kinetic energy is associated with the fluctuation in velocity within the fluid, and its magnitude provides information about the turbulence level. The exported data from the numerical simulation unveils critical insights into performance of two propellers operating under different conditions, especially the analysis compared the efficiencies achieved in two scenarios. The non-multiphase condition, where the simulation simplifies but by not explicitly considering multiple fluid phases, and the multiphase condition, which incorporates a more comprehensive model accounting for phenomena such as cavitation. The first was non-multiphase condition efficiency, which was 26.47%. In the absence of explicit consideration for multiple fluid phases, the simulation yields an efficiency of 26.47%. This scenario represents a simplified modeling approach, providing a baseline for propeller performance without detailed consideration of complex fluid interaction. Conversely, when the simulation includes a multiphase model accounting for phenomena like cavitation, the propeller's efficiency increases notably to 33.71%. The improvement underscores the influence of accurate representation of fluid behavior on propeller performance, particularly highlighting the impact of cavitation. The observed increase in efficiency when incorporating multi-phase modeling emphasized the critical role of accurately representing complex fluid behaviors, especially cavitation in propeller simulations. Cavitation, characterized by the formation and collapse of vapor bubbles, significantly affects the propeller performance. The results underscored that a more comprehensive modeling approach enhances the understanding of real-world propeller dynamics. The findings hold practical implications of engineers and researchers engaged in propeller design and analysis. The increase in efficiency under the multiphase conditions suggests opportunities for optimization. Engineers may explore adjustments to propeller design, refine operating conditions, or consider specific fluid properties to further enhance performance. The study contributes to ongoing efforts in propeller optimizations and advancement of marine propulsion technologies by highlighting the impact of multi-phase modeling on efficiency. The results provide valuable insights for refining propeller designs and improving their overall performance. That's all for our presentation. Thank you so much.